And we are now recording. So let's get the slideshow set up from the current slide, and we'll go from there. Okay. All right, we were using this slide before. It's an illustration of Hooke's Law. And I won't go over all that again unless you have questions about it. We were doing example 1 on page 366. That's in section. No problem. Oh, I forgot to check that door this morning. Yeah, surely. Sorry, I forgot that. Okay. Assuming a spring constant is example 1. Assuming a spring constant K is equal to 400 newtons per meter. Find the work required to compress the spring 10 centimeters beyond equilibrium. We did that problem, the A part, last time. Any questions on that? Okay. The B part, same type deal here. And by the way, before I get too far along here, this reminds me it's time for my advertisement here. Hooke's Law, named after the English scientist, inventor, architect Robert Hooke, made important discoveries in physics, astronomy, chemistry, biology. Sorry. Quite a broad character here. Pioneer in the use of microscope to study organisms. However, I guess he didn't get along with everybody all that well. Got in several bitter disputes with other scientists, most notably with his contemporary Isaac Newton. And guess what? No matter how good Hooke was, and can be remembered for a lot of really positive things, that's a pretty heavy weight to try to fight against, is Isaac Newton. He's going to win most of the time. Newton was furious when Hooke criticized his work on optics. Later, Hooke told Newton he believed Kepler's laws would follow from an inverse square law of gravitation, but Newton refused to acknowledge Hooke's contributions when he wrote his masterwork Principia. Shortly before his death, Albert Einstein commented on Newton's behavior. That, alas, is vanity. You find it in so many science knowledge the work of Kepler. Or Newton, maybe he meant also did not. So, just a little blurb there, but here's the point. You could write on Hooke, you could write on Hooke's Law, you could write on Newton, you could write on Kepler, you could write on Einstein, okay? And then this Principia, Newton's work. I mean, there's just tons of things in that one little blurb that you can pick as a paper topic. Hint, hint, get working on your paper. Okay, that was the reason for the commercial break there. All right. I'm sorry my head is clogged up, and it was better, but it's hard to... Okay, let me see. Yep, I need to change the black. All right, so here's the C part. We are assuming a spring constant, so let's draw a little picture. We'll use one of those. This K here in the formula, we're going to have as 400 newtons per meter. That's the spring constant K. Okay? Now, the B part says, find the work required to compress the spring 2 centimeters more when it has already been compressed 3 centimeters. So this was a extension. This time we're going to be compressing the compressing the spring. Now you start with it at 3 centimeters compression and then find the work to go from there to an additional 2 centimeters. So 2 centimeters more. And we've got the silver here. So we have all of my attendance because they finally dropped Muhammad Nobu, however you pronounce his last name, Jobu, from the thing. I know his wife was having some health problems and he wasn't sure if he was going to make it this term, so he held off paying and evidently decided not to do so. He's not here, so 3 for 3, 100% attendance. Way to have it. Which, for a lot of the term, y'all have been all three here. Okay. So we're compressing the spring from 3 centimeters, an additional 2 centimeters, which takes it to 5 centimeters. Okay, compression. Okay? Sorry, my head is so clogged up. Well, what we're going to use is the definition for work, which we used before, which is work, and that's what they're asking for. What is the work to take it from there to there? The work performed in moving an object along the x-axis from A to B by applying a force of magnitude f of x. This work is the integral from A to B of f of x dx. Okay? That works for any variable force. Spring force is a variable force. So in this problem, what's our A to B here? Here's 3 to 5. You got it. So the interval will be from 3 centimeters to 5 centimeters. And the force is this right here. Now you really don't have to include the minus sign. You're going to be doing work, so it's going to be positive. So the k here is 400. That can go outside the integral, okay? And then the x goes inside the interval, so you have x dx, okay? The force is 400x. You can pull the 400 on the outside and do it. Sorry about my head. Goodness gracious. So what will this give you? 400. And then what's the antiderivative of x dx? X squared over 2, evaluated from 3 to 5. All right? So it'll be 400. And actually the 2 can be taken out with the 400. So, because that's not what I meant to do. Let me get my pen back. I meant to do this. The 2, and that would be 200. As long as, there's nothing else involved here, the 2 can be taken out too. So those will be 200 times, what would be the next part? A little louder? Okay, 25 first. 25 minus 9. So this will be 200 times 16, and that would be 3,200. And what units? Okay. Yeah, this was Newton per meter. That's meters squared, so it'd be Newton meters. And does anyone know what a Newton meter is? Joule. A Newton meter is a joule. Okay? So that's what we got. Let's see what they did. Oh, man, I forgot it again. I got it right on the first time we did it. I ignored it here. I wrote them in, but I didn't notice it. Notice this is Newton per meter, but this is in centimeters. So we got to get this into meters. Botched it. Sorry. How many meters is 3 centimeters? 0.03 meters, and this would be 0.05 meters. Okay? That's what our limit should be here, not 3 and 5, 0.03 and 0.05. So, when we do this, sorry about that. Let me erase a bunch of this here. Actually, not going to be as bad as probably what you might think. All right, let's go back and do this. .05 squared would be 0.0025. You have to have 4 decimals when you square it. Minus 0.03 squared would be 0.0009. Again, you have to have 4 digits, 4 decimals. When you subtract those two, you get 0.0016. And when you multiply that, the 200 basically will wipe out those 2 zeros, so your decimal goes there, and this will be 0.32 Newton meters, which is 0.32 joules. Guess what? That's a mighty small amount of energy, okay? Because a joule by itself is a pretty small amount of energy, and then less than a third of a joule is really small. But that is the answer. Sorry, I didn't catch my units there. Units are your friends. Pay attention to them. You know, ignore them. All right. Sorry, my head is just so clogged up. I don't know if it's the room that makes it worse, but after the last class, down in cleared major type. But sorry about being hard to understand. All right. Any questions about that before I go to the next slide? All right. Here we have a situation. Again, variable force situation. What we're trying to do is build a column. This is example 2, building a concrete column. Compute the work, against gravity, having always to work against something, against gravity required to build a concrete column of height 5 meters, and that's what you're going through here, the picture here, and a square base of side 2 meters. Now, frankly, that doesn't look like a square to me, but they've labeled it as if it is. Here's 2 meters here, 2 meters there. Okay, it looks like we have that backward a little too long. That looks more rectangular, but yeah, from the right perspective, that's a square. Yeah. So that's, each square is 2 by 2 meters, 4 square meters. Okay. Now, we're going to assume that the concrete has a density of 1,500 kilogram per cubic meter. That's the one thing they don't show on here, and of course, as soon as I go to write, it's going to reduce, so I can't write without reducing. I don't need this, okay? So let's write this. The density of the concrete is 1,500 kilogram per cubic meter. And that is the SI unit for density. It's kind of a ridiculous unit. I mean, a cubic meter is a huge amount. A huge amount. Just a general idea. Let's just say this is approximation. This doorknob here, maybe I'll let you see this better. This doorknob is about a meter off the floor, which makes the door maybe not quite a meter wide. But just imagine from this, and then come a meter out here, that's about 1, 2, 3 feet, somewhere about here. That is 1 cubic meter. What if that was all concrete? That block I just described. That is a lot of mass. 1,500 kilograms, which is approximately, this isn't exact, but approximately, what is exactly 1.5 metric tons, which is very close to the tons that we're used to dealing with here. So those are awfully close to each other. So that's a lot of concrete. So to me, the more reasonable thing is grams per cubic centimeter. That makes a lot more sense. Grams, cubic centimeter would be about the centimeters about the width of your little fingernail. So that would be like a sugar cube. How many grams in that? That's something I can handle and play with. But they use the metric one. Huge number, 1,500 kilograms per cubic meter. Okay. That's not really a big part of the problem, but just why it has such a big number. So, compute the work against gravity required to build the concrete column. Okay. So, what we're going to imagine, this is kind of like a Riemann-Sum type problem. What we're going to do is imagine each slab you put in there is the work that you're doing against gravity. This really is adding up like Riemann-Sum. Okay, the total work is the sum of the work performed for each layer of the column. Okay, now they don't say here, I don't think, yeah, they don't say what the thickness of the layer is. They're just calling it delta y, which is, this is the vertical axis, they call it y-axis. So what we have is our dy's here. Okay, so what is the work to perform on each layer of the column? Now, technically, that first layer that you put there is work free. Yes, tell me that. It's a 2 meter by 2 meter times delta y. That's your thickness. That would be your volume of that first layer, but you're not having to lift it at all. You just slide it into place. And as long as you have perfectly greased floor or surface or whatever, it slides with almost no work. The next one, though, you're going to have to lift delta y height. So you're going to have, because you've got to go on top of that first one. So it would be 4 delta y times that. That would be how many kilograms? Okay, because 4, 2 times 2 times delta y, that gives you your cubic centimeters. Multiply that by your density, which is kilograms per cubic centimeter. Then multiply that by your acceleration due to gravity. That's what you're working against. That's acceleration due to gravity. Y'all know it from physics, don't you? 9.8 meters per second squared. That gives you the amount of work in newtons to lift that next one up on top of that. Then the next one's going to be lifted 2 delta y's, because you got to go on top of that. The next one, 3 delta y. So every one is increasing 1. You're summing that from 0 to 5 meters. So that pretty much is your, describes what's going to be our Riemann sum, which will then be our integral. So what are we doing? We're lifting 4 delta y, that's the volume, right? 2 meters by 2 meters by delta y meters. Lifting it a height of y. Now y is your variable here. It's how high you're lifting this. Here was just 1 delta y, 2 delta y. Your y is just how high you're lifting. In, that was meters, wasn't it? 5 meters high? I believe that's right. Yeah. So that's a pretty tall column. Okay. Catch this. About how tall am I? In meters? About 2 meters. 3 feet, 6 feet. Okay. Meters a little bit beyond that. So the room here is another, about 1 more meter high, right? A little, maybe not quite as high. So basically a 3 meter tall room. The one below us is 3 meters. So if that's 3 meters, then it would come up 2 more meters. So it would come up from the floor of the beneath us to here. That's how high this column is going to be. That's a pretty decent column, especially 2 meters on the side, 4 square meters. I hope this is the testing of the alarm, right? Is it the time of day? Okay, good. I was hoping it didn't look like any bad weather out there. So you're lifting at y units. So this is the volume of each thing. Multiply that by the density of each slab. That gives you the mass of the slab. Multiply that by the acceleration due to gravity. That gives you the weight of each slab, and you're lifting that y units. So that time y. Okay? There is your force times your displacement. Okay? That's going to give you your work. So if you look at this, that's going to be the integral from 0 to 5. Now what goes out front? The 4 is out there. The rho is out there, 1500. And your g is out there at 9.8. I just didn't leave enough room. 9.8 meters per second squared. Those are all constants, and what you have inside is y dy. Way we're setting up delta y's, but that's what you get. Okay, as you let that thickness get smaller, 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 Riemann zone becomes that. How do we solve that? Well, 4 times 1500 is 6,000, right? 6,000 times 9.8 is going to be 50-some thousand, right? Second? 58,000. Oh, 800. 58,800. Okay? 58,800. That's out front. What's the antiderivative of that inside? Times y squared over 2. Evaluated from 0 to 5. Okay, again, you can get rid of the 2 into this will be 2,9,400. Okay. And that's not going to be too bad of an integral to do. 29,400 times 25 minus 0. So this gives us, oh boy, someone with a calculator. 7,000 something? Second? Yeah, 29,400 multiplied by 25. 735,000. What units? Should be joules. Work in the SI system should be joules. Now, if you didn't like writing that big a unit, you wanted that big a number, you could have chosen a bigger unit. That could have been 735 kilojoules. If you wanted a smaller number with a bigger unit, move it 3 places. All right, let's see what they got. 735,000 joules. Yeah, they didn't do that last part, but I did. Now, I did not really care that much for their presentation of how they did it. To me, it really went around your elbow to get to your ear, and I thought, why take it all that many steps in there? Why don't you just deal with it as we did? And maybe my way is confusing to you and their way is better, whichever way suits you better. But if you take the volume of this cube, which is easy to do, 4 times delta y, that's what we got here, multiply it by the density, that gives you the mass of that slab, multiply that by the acceleration due to gravity, that gives you the force of the slab, and then multiply force times displacement. That's the work of doing to build the slab, and you're summing that over all the things. To me, that's pretty straightforward, and you already know what 4 and rho, they gave you rho, and g is. Then the y delta y is what you're doing. To me, that's easier to see than the way they did. But if you don't see my way and you want to use theirs, by all means do it. All right, so that was one example of a variable force. Spring is a variable force, and then when you're building something that the higher you go, the more work you have to do. Makes sense. then if you, I think one of the, in a sense, one of the worst jobs that I can recall is hauling shingles up a roof, up a ladder to a roof, and deliver them to the guy who's laying the shingles. Oh man, because the higher you go, sorry. The higher that you go, the more you're having to work, to get that, next one up there. And it's the same type of problem as this. Another one is hauling concrete as people are building a building. And the higher they go, the more you have to wheelbarrow that up to them as they're laying the blocks. Those are some hot, hard jobs. Variable force, because the higher you go, the further you have to take it. Okay, here's another kind of example like this, except this time we're taking water. I'm sorry. Here's how they approach the problem. And again, there's nothing wrong with their approach. I just don't find it particularly clarifying. Okay, the work lifting a layer to height Y, and there's that 58,800 that we got, times delta Y times Y. So that is exactly what they did. Why do you turn around and call that some L of Y? To me, that does nothing for me. Use this. I mean, that makes sense. Just move the delta Y on the outside and this on the inside, and you got it knocked. Why introduce another function here? I guess that's the lifting function or something. I guess it's just to make it look like the spring function, but it's not the spring function, so why make it look like that? But if that's how you see it and it helps you, go for it. Use it. It's good. Okay. Now, this is part of what they're going to use in this problem. Pumping water out of a tank. And actually, here is the figure. Okay. I'm sorry, I hit the wrong button here. My head is clogging up, and it's just hard to think. It's hard to keep straight where I'm trying to go here. I can't breathe. All right, here's your picture. Here is a spherical tank. When would you ever have a spherical tank? Have you ever driven down 65, going south, past Chilton County, into Chilton County? What's the capital of Chilton County? Oh man, all I can think of is Jemison. That's not the county. It's the place where they grow all the peaches. Starts with C2, I think. I can't think of it. But have you ever noticed the water tower there? Shaped like a peach, which is basically a spherical tower. They put a little stuff in it, that's not all the water, to make it look like a peach. Y'all never notice that? Going south on 65. Okay, next time you go south on 65, you go through Shelby County, and the next county south is, I can't think, it's Chilton County, but I cannot think of that town that has the peach. Famous peach. Because they grow a lot of peaches there, and they're good peaches there too. So, yeah, they have spherical tanks. So if you're pumping water out of a tank, a spherical tank has a radius 5 meters, okay? And they're not showing that anywhere here except this capital R here. And of course, when I go to write on it, it's going to shrink. Okay, this capital R is equal to 5. That's the radius of that sphere, and that's in meters. Which again, from the first floor up to about my height here, that's going to be your 5 meters, but that's the radius. So you had a tank that's, if we had a 3-story building here, then that's going to be about 15 meters. So that'd be a little bit more than what you have. 5 meters, 10 meters. Yeah, that would. No, yeah. 3 meters floor. Yeah, a 3-story building. You could fit, in fact, the part down there of this building. Imagine a spherical tank that went from the bottom of the first floor to the top of the 3rd floor. That is the size tank. Pretty good size tank. Okay? All right. It's filled with water. Calculate the work performed against gravity again in pumping out the water through a spout at a height of 1 meter, through a spout of height 1 meter at the top. So in our new book, new edition, they have the spout. In the old edition, they didn't have the spout. So I'm going to try to draw the spout in here. There's your spout, okay? And this is 1 meter from the top, okay? So you're going to pump another meter up. The density of water, so rho for water is 1,000 kilograms per cubic meter, okay? So again, picture that cubic meter you have back there. That cubic meter filled with water literally weighs a ton, or very close to it. 1 megagram is the mass. That would be equivalent to, it's called 1 metric ton of mass, which is equivalent to 1 English ton of wood. So that's hot. But then that's a cubic meter of water, okay? The density of water is that, okay? So what we want to do is calculate or talk about how high we're pumping the water. That's what you're having to do, work against gravity. Let's cut that sphere into slices, horizontal slices here, and every slice is going to be a dy, right? So how much are you pumping the water? Well, this is you got several things that you're having to do. The height that you're pumping it is going to be your y, and that height is going to be 1 when the water is at the top, because you got to pump it 1. Then for the next layer, it's 1 plus delta y, and the next layer is 1 plus 2 delta y. So basically, the height that you go here, in this they measure y equals 0 to the center of the tank, which is a little bizarre because you got 1 more than the depth of the water here. But the depth of the water, using y is equal to 0 to be the center of the tank, then you're going to have to do some thinking through on what that distance is going to be, okay? Now, here's how they're going to set up. And there's several fronts to this problem. And what it looks like they're doing first is calculating the volume of that disk of water. Okay, you're going to split this into disks. So let's do that first. That seems to be where they're focusing first. So the volume of this disk of water is going to be, I know the thickness of that disk, that's delta y, or dy we'll later call it. Okay? The radius of that disk is not the radius of the sphere. That's only right down here at this radius would it be 5. So up here it's going to be something less than 5. This is 5, but what this radius is here is less than 5. And that radius from Pythagorean theorem Now again, they're measuring from the center of the sphere, and that's going to be y here. So that's going to be, this radius here is r squared minus y squared, Pythagorean theorem. Okay? So little r here would be the square root of r squared minus y squared. So that's the area of that sphere, of that slice. The thickness of the slice is your delta y. Okay? So that'll give you the volume. Area times thickness gives you volume. So that's going to be your area of that is pi times this radius squared. Well, this radius squared is going to become then r squared minus y squared. So it's r squared minus y squared. When you square that little r squared minus y squared times dy. So that is the volume of that sphere, of that slice. The volume of this slice is going to be pi times r squared, that's the radius of the sphere, minus y squared, which is how high you are above the center. Okay? Now, when you get down to here, in these lower parts, again, that's going to be your radius, and it's just your triangle is turned over down there, but it's still going to be the same thing. So we're okay with that. That's going to be the volume of every slice is pi times r squared minus y squared. Okay? And when this y is 0, that's just going to be that slice that's right through the center of the sphere. And that would be exactly that. All the rest of them are going to be a little bit smaller. So that's the volume of the slice. Multiply that by the density, so you have the mass of the slice is going to be pi rho r squared minus y squared. That's the mass of the slice, which is mass is volume times density. Okay? Now, multiply that by the acceleration due to gravity, because you have to work against gravity. So mass times acceleration is then the force, or the weight of each slice, is going to be pi rho g times r squared minus y squared. All these are constants. Y is your variable. R is even a constant. Okay? So that's going to be the weight of each slice. Now, how far do you lift each slice? Okay? Now, you know you got the 1 at the top, and then you've got, for this height y right here, this height y, how far you're going to have to lift this slice is r minus y, right? R is the distance to the top minus the y from the center, so you're going to have to lift it. R minus y plus 1, because you're going to have to lift that extra 1 meter. So the distance that you're lifting, and remind yourself, you know what I left off? I forgot to put my delta y in here. There's a delta y there, delta y here, and delta y here, because that's the thickness of the slab. I said it, but I didn't write it down. Okay. Now, this is the weight, and your work is force times, and this your force. You could also call this the force due to gravity, which is the weight of that slice, and that times your distance, that's going to be your work. So the distance that you're doing is, what do we just say? R minus y plus 1. So the work is R, this is your capital R, minus y, plus 1, sorry. Let me clean up that a little bit. I don't really need the parentheses there, so let's take them out. R minus y plus 1. Okay. That's going to be the distance you lift times your force. Pi rho g r squared minus y squared dy. So that's what we've got to integrate. Okay. Kinda. Okay. So the work is going to be the integral of, let's pull out all your constants, pi, rho, and g. Pull all those out, and then you're going to integrate by dy from, now, what is your y going from here? Your y is going from minus r to plus r. Okay, right? Y is going from minus r to plus r. So, minus capital R to plus capital R. Not your little r, that was the radius of that slice. That's not what we're talking about here. Okay? You got the pi rho g on the outside, and then your multiplier, your integrand is r minus y plus 1 times r squared minus y squared. Okay. Now that's an awkward seeming integrand. Let's see if there's anything that we can do. Oh, and by the way, the r is 5. They're going on and taking care of that. So let's clean that up and put that in here too. Okay, so this will be pi, your rho is 1,000 kilogram per cubic meter. Okay, times g is 9.8 meters per second squared. Alright, so that's the stuff out front. Integrating from minus 5 to 5 meters. Your integral here, this is 5, right? Plus 1, so that'd be 6 minus y times 25 minus y squared dy. Alright, now frankly, don't try to integrate like this. Go on and multiply those two together. What does that give you? 6 times 25 is 150 minus, second? Okay, you can do that. 6y squared. That would be this one. And minus 25y. And then you got a plus y cubed. Right? That's what we're going to integrate. So let me shorten this as much as possible. 9.8 times 1,000 would be 9,800 times pi times the integral from minus 5 to 5 times this integrand. And I'm going to rearrange it and write it as y cubed minus 6y squared minus 25y plus 150 dy. Okay? That'd be 9,800 pi times antiderivative of y cubed. Oh, man. Y to the 4th over 4 minus 2y cubed. You've already divided by 3. That's why you got 6 down to a 2. This will give you a minus 25 over 2y squared. Okay, it takes a while for it to catch up. plus 150y. Evaluate that from minus 5 to 5. Now notice this is not one of these integrals that you can say, oh, well, it'll just go 0 to 5 and double it. Why not? There's more work to get these flipped out than there were to get these flipped out. So yeah, it's not equivalent. So you can't do that shortcut. Don't even think about it. Okay. You didn't. So here we have to plug in numbers, and they are going to be a little bit messy. I don't know where to write them. I think what I'll do is erase some places here. Let's see where I'm going to erase. I guess we're okay to erase all this up here. We've already used it. The eraser is so slow right now. Okay, hopefully this will give us enough room. So let's do 9,800 pi times, okay, we're going to plug in 5. Yuck. Okay, 5 cubed is 125 times another 5. Well, you tell me what 5 to the 4th is. If you got a calculator, plug it in. It's 125. 625? Yeah, that's 625 over 4 minus 2 times 125, that would be 250, right? Minus 25 times 25 is 625 over 2. Okay. Plus 150 times 5. That will be 750. I think. Is that right? Okay. That's your plus 5, huh? Now we have to plug in a negative 5. I'm sorry?
7,500, right?
Oh, 7,500. I left off a 0, didn't I? Yeah. Let me think, make sure of that. No, it's just 5, isn't it? Wasn't it at 150? Or is that where I messed up?
Yeah, why you forgot to put the...
I'm sorry?
You forgot to put the 0. That it's not 150.
Okay. When we multiply 6 times 25, didn't that give us 150? I think it was. How badly have a... Okay. Okay. You're trying to get more money out of me, I can tell. Okay. Yeah. Yeah, just move those decimals. Do you work for Wells Fargo? No, never mind. I'm just kidding. Okay. All right. Now that's the plus 5. When we plug in a minus 5, we're going to be subtracting. So that's going to give us, this will just be a minus 625 over 4, because when you square or raise negative 5 to the 4th power, you get the same thing. So those are going to go out. But then we would have plus, because minus a minus is plus, 2 times 125 is, so that would be a minus 250. Why are my minuses adding up and my pluses disappearing? I don't like this, okay?
Why
What's that? Yeah, you can do it on there. We'll see if we get the same answers. Okay. Then we'll do, this will be a plus 625 over 2. And this will be another plus 750. Okay. All right. So these go out. Okay. And this will be a, that will be a 500 plus 500. That'll be 1,000. So I get 9,800,000 pi. 9.8 million pi. I hope that's right. That seems like an enormously large number, but that is a. Yep, that's exactly what it is. 9,800,000 pi joules. Okay? Yeah. So we did get the same answer. That's a lot of work. The other one, remember, was 0.3 something joules. Yeah, that's not very much. 0.32 or something like that. This is a lot of joules. 3 times that is going to be more than, awfully close to 30 million joules. 30 megajoules of work to pump that water out of that huge tank. Of course, it's a huge tank, and yeah. So pretty big size number. That's the last. Any questions on that? Of 6.5. You want to do the preliminary questions? Do? Okay. So let's clear these and do the first. I'll just use this same slide so I don't have to mess with something else. Why is integration needed to compute the work performed in stretching a spring? Why is integration needed to calculate the work in stretching a spring? You don't need integration if you say, I'm going to lift this chair and carry it over there. It's just force times the distance. But why is stretching a spring, you do have to have integration? Lifting the chair requires the same force no matter where I am. To lift it another foot, same thing. It's just, that's a constant force. A spring, though, is a variable force. Because when you stretch it a little bit, that's a little bit of force. You stretch it more, it's going to be more force. Stretch it a lot, you got even more force. That's a variable force, not a constant force. Now that's the reason physically in my mind. Let's see how the book explains it in this context. Because the force required is not constant through stretching process. Yeah, saying the same thing, it's a variable force. Number 2, why is integration needed to compute the work performed in pumping water out of a tank, but not to compute the work performed in lifting the tank? So, pumping water out of a tank is going to require integration. Lifting the tank is not. Basically, it's the same thing. Lifting the tank is a constant force, right? It's the weight of the tank. But pumping water out, you've got to lift it. Now, this time it's not a variable force, it's a variable distance. Remember, work is force times distance. Variable force, you got to do it. Variable distance, you got to do it. Because you're pumping the first part a little distance, next part further distance, further. So there you have a variable distance. Now that's how I express it. Let's see how they say it. The force involved in lifting the tank is the weight of the tank, which is constant. That's all they say. They don't say the other. The other is that you got a variable distance to lift. Okay. Number 3. Which of the following represents the work required to stretch a spring with a spring constant K, a distance x beyond its equilibrium position? So here are your choices. Kx minus Kx 1/2 mkx 1/2 mk squared is what I meant to say. 1/2 kx squared or 1/2 mx squared. Okay? The question is, which of the following represents the work? Which of those represents work? 1/2 kx squared. Okay? Kx represents the force, right? And minus kx is the restoring force. Okay? Those are forces, they're not work. 1/2 mkx, m, is it k squared? Is that what did I write that right? Yeah, mk squared. That's just kind of nuts, okay? I don't even know what m is. I assume it's mass. They didn't tell us in the problem, but if it is mass, why would you square the constant? You know, I mean, that makes no sense at all. 1/2 kx squared, yeah, you're integrating with respect, you're integrating this force, and that gives you 1/2 kx squared. So that's exactly right. The next one, 1/2 mx squared, makes no sense either. Mass times the distance squared doesn't give you work. Okay, so don't even try. Okay, so that was number 3. Number 4, what does it mean when the integral used to calculate work gives a negative answer? What does it mean when the integral used to calculate work gives a negative answer? Second? Okay, basically then, what you're calculating with the integral, what normally you count the work you do to make it happen, that would then indicate the system is doing work. You know, in other words, that would be like the water falling off a dam. That's doing the work to turn the turbine rather than you having to lift the water up. You know, so yeah, it's one way of saying it's a negative work. But when the force applied is in the opposite direction to the motion. That's another way to say it, which is not really what I... Okay, homework exercises here. Do number 1. Do either 3 or 5, or both if you choose. Do number either 7 or 9, or both. Either 11 or 13, or both. Do 15. It's the only one quite like that. Second? 15, yes. Any of the odds 17 to 21. And then I would say any of the other odds 23 to 37. You might want to do one or more than one of those. It's up to you. Now they have a little blurb here, and the further insights and challenges, of work energy theorem, which you probably hit in physics, and you certainly should have, and talking about escape velocity when you're dealing with leaving the gravitational attraction of the Earth. You may not have hit that. You may find that interesting to pursue. So that might be another potential paper topic or two. And that finishes Chapter 6, Applications of Integration. Now, since we did finish Chapter 6, I hate to do this to you, but I'm going to do it. I think I am anyway. Here is your second test. Now, the only reason I say I hate to do it is I don't have any of your first tests in yet, but hopefully they will be coming, right? So here are your second tests. Okay. All of you did get a copy of your first test, right? Okay. And you are going to be turning those in really soon, aren't you? By the way, you weren't here, but we worked or set up some of the problems from the for the first test in the last screencast-o-matic. So you did? Okay. Was it helpful? Okay. All right, good deal. Okay, and that does finish chapter 6. Let's move on to chapter 7. If I can get this to respond. There we go. All right. Let's see, we've got another 20, 30 minutes. Okay. That's the good news, isn't it? Okay. All right. Let's get started on chapter 7. Now, to me, chapter 6 and chapter 7 are the big main things in Cal 2. Substitution from chapter 5, yes, and then techniques, applications of integration, techniques of integration. When we get to chapter 8, there's just a couple of sections. It's real short, but that's also kind of important. From there on, chapter 9 is differential equations. We don't do that here. We do it in differential equations. But then 10 is infinite series and sequences of series, and 11 is some vector stuff, which is all good stuff. It's important stuff. But this, to me, is the heart of what Cal 2 is about. Applications of integration and techniques of integration. And I can't get this to open. There we go. So let's go to 7.1. Now you notice this is a long chapter. Lots of sections. Now we're not going to do them all. They're not going to do anything if they won't open. Why are they sitting here like this? I did this before. PowerPoint is such a pain in the neck. Goodness, I'm getting hungry too. I don't know why. On Tuesdays and Thursdays, I have. I don't know why. This is my early days, so why am I hungry now? Here we go, finally. Okay. From current slide. All right. This is a, you can't quite see it all, can you? I'm going to cut off some of the sky here so it just gets blown up a little bit more. Okay. Just a pretty picture, but it also shows some of the stuff you can do. This is a computer simulation of the Indonesian tsunami that happened back on December 26, 2004. I guess all of you were alive then, right? Okay, barely, huh? Were you in?
My country, yeah. It affected my country.
Okay, India or
Sri Lanka.
Sri Lanka? Oh, that's right. You told me that. Yes, it slammed into Sri Lanka. I know we have friends in from used to be Madras, which is now Chennai, India, down in Tamil Nadu, and they had relatives that were on the beach that day, and they didn't hear from them for several days, and they weren't sure if they were going to be alive or not. Yeah, but I think they all were accounted for. A lot of people didn't make it. It just came all of a sudden. And Sri Lanka got it pretty hard too on the East Coast.
East.
Yeah. So were there a lot of casualties, or do you remember? Were there a lot of casualties from that, or do you remember?
We got a lot of people die at the west side and the east side, and it hit pretty hard.
Yeah. Yeah. And a lot of the people who live real close generally could be quite poor. Yeah.
It came especially early in the morning.
Oh, was it? Yeah.
So
It was a Sunday morning too, wasn't it?
Yeah.
Yeah.
And most of the people were asleep.
Sleeping. Oh,
Yeah.
bad news. Yeah. Those living real close, they didn't have any warning at all. Yeah. So this was going toward Indonesian. Well, I don't know which way was it going. They don't show. But this was that tsunami. It went both directions. It slammed into Indonesia, and I think as far north as Thailand, and then made its way all the way across the Indian Ocean to hit India and Sri Lanka on the other side. So yeah, it was pretty devastating. And this was 8 minutes after the earthquake, created using models of wave motion based on advanced calculus by Stephen Ward, University of California, Santa Cruz. So just an example of how we can use the calculus we're going to be talking about. Not necessarily in this chapter, but some of it I bet you did. All right, now, before we get into the first technique, and by the way, substitution is a technique of integration. That's why we covered that in chapter 5, because if y'all hadn't had that, you needed it before you got here. Then they had the applications. Now we're going back and doing more techniques of integration. Okay, before we do, let's remind ourselves, because I know you've done this before, what if you have a product of two functions, u times v, and you want to take the derivative of that product, d by dx. I don't need a tick. What? This is so aggravating. I click on this and nothing happens. Okay, there we go. D, I have to go back. Okay, d by dx of a product function. What does that give us? Second? I couldn't hear. Yes, the product rule. And what would that be? Did you say du times v plus v times du? That's it. Okay, what we're going to do is write this in what they call, the way, because you gave it to me that way, we'll write it in differential form, not derivative form. Yeah, that's it. You hit it on the nose. Okay? Now, from that is suggestive of what we are going to be doing, and that's this. What if we have an integral that we are having trouble doing? And that integral is made up of a product. For instance, v du. Okay? If we can separate what's inside the integral into a function times the derivative of another function, then we can simplify that, and if we can integrate, well, we don't even have to integrate, that's going to give us duv minus u dv. Okay, I hope I have the things in the right place. And then if this is what you're trying to integrate, and that's a hard thing to do, when you integrate this, you lose the d here, and you use that, and you just have uv minus this integral. Okay? And that's what the integration by parts says. That if you're trying to integrate a function, I did it backwards, sorry about that, u of x times v prime of x. That's, put this over here. In fact, let me do that. So it'll be saying it the same way. Okay. Okay. Let's see if I can get it right this time. U dv is a okay, that's it. If we're trying to integrate something, and that's a very difficult thing to integrate, if we can split this into a u and a v, a u and a dv, and we take the derivative of the u and get du, and integrate the v dv and get v, then we have u, we have v, write that out front, subtract from that the integral of v du. Now, why would we want to do that? Under what circumstance would that be feasible? There may be a couple, but here's the main one. Usually, when you take a derivative of a function, you get a simpler function. Not always, but usually. Okay? Usually when we integrate a function, it gets a little more complicated, but not always. So, if you can find a function that's going to get simpler when you differentiate, and another function, the other part of this, that doesn't get any worse when you integrate, then it's the product of those two functions, whatever they are, minus v du. Well, the v is simpler, is no worse than this was, and this is simpler than that was. So yeah, that might be easier to do. That's the key. So here's the integration by parts formula. If you can break your integrand into a function times the derivative of another function, then figure out what that other function is, the v, and that'll be u times v minus the integral of v du. v du. And if this got simpler when you differentiated it, which most of the time it does, and this didn't get any worse when you integrated it, which a few functions you can do that to, then this is usually going to be easier to integrate than that. Guess what? If it still gives you a problem, do it again. You know, and keep doing it until you get something you can get done. That's going to the next step. But that's integration by parts. Okay? And frankly, doing it, I think, is easier than that formula. So let's do example 1. Now, example 1, okay. Let's use this slide. Okay, so let me erase all the ink here, and let's do example 1. Evaluate this integral. X cosine x dx. Okay? Now, do any of you know how to integrate that function right off the top? Me either. That's not one of the ones. You can't substitute, you can't. There's nothing we can do that we have tools yet to do that. So and it is a product, right? So let's see if integration by parts is going to help us in here. Now, it's a product of two things, x times cosine x. Now, we can put the dx with either one of those we want to. They're going to have to go one way or the other. Now, when you integrate, when you differentiate x, does it get simpler or more complicated? Differentiate. Simpler. Derivative of x is 1, right? Okay, so yeah, that gets simpler. Now, when you integrate cosine x, does it get, it's about the same thing because that's going to give you a sine. Okay, that's no worse. So I think that's the way they need to go. So here's where we start. Almost sounds like a substitution. It's not quite, but it starts that way. Let u equal x and dv equal cosine x dx. Whichever one is the d part has to have the dx with it, right? So then, what is your du? 1 dx, right? In differential form, right? Okay, what about the v? That basically is an integration of dv. What would that be? Not cosine, sine. Sine x. Because when you take the derivative of sine x, you get cosine x dx. Okay? Now, okay. There's our setup. Where we go from there is take the functions without the d's in them, the functions themselves, and multiply them together. That's just going to be x sine x, right? Minus the integral of your bottom line here. And that's going to be sine x dx. v du. Okay? I think we can do that one. So this is x sine x minus, what's the antiderivative of sine x? Negative cosine x, so this will then be a plus cosine x And then because this was a plus c. I'm trying to think what you call that. Indefinite integral. Because it's an indefinite integral, you have to use a plus c. Now, this is saying the integral of this is equal to that. Which means if we take the derivative of this, we should get this. Right? Well, let's see if we do. Take the derivative of this, you get, that's a product, so you'll have what? X times cosine x plus sine x. Take the derivative of this, you get minus sine x. So plus sine x minus sine x goes to 0. Take the derivative of c is 0. You get x cosine x. Yeah, it did work. Good deal. So that's integration by parts. See if you can split it into a product of two functions. The function that gets simpler when you differentiate, let that be your u, and the one that doesn't get much worse when you integrate, let that be your dv. Okay? And go from there. All right? And they got x sine x plus cosine x plus c. Good for them. Okay. And then they differentiated, and they sure got the same thing. And they talk about getting simpler or more complicated. Same thing we did. So I think we're ready for example 2. Want to try it? Okay. I think I'll erase this one if that's okay. Okay. How are we doing on time? Okay. 10 more minutes. Oh, we got plenty of time. Okay. Here's the this one. The integral of x e to the x dx. That's obviously a product. Oh, wait. First, can you do that integration right off the top? No, I can't either. Okay? So, it is a product of two functions. Okay? And let's see. Will one of those get simpler when you differentiate and the other not get any worse when you integrate? Which way? Okay, just like we did before, let u equal x and dv is equal to e to the x dx. Keep the d's with each other, okay? Then, what do we get? du is equal to dx. That was easy enough. And how about the v? What would v be? E to the x. When you integrate e to the x or differentiate e to the x, you get c to the x. I'll take that anytime. Okay? Now, what do we do next? U times v. So we'll do these two, product of those two. That's going to be x e to the x minus the integral of your bottom line here. And what does that give you? E to the x dx. I think we can do that one. This will be x e to the x minus antiderivative of e to the x is e to the x, okay? And then you need a plus c because it's an indefinite integral. There it is. Way to go. And you can differentiate this if you want to, if you get back what you had to start with. When you take the derivative of this, what do you get? Second, e to the x, when you take the derivative of this is 1 times e to the x, plus x e to the x, okay? Then when you take the derivative of this, you get minus e to the x again. Well, the plus e to the x minus e to the x, they disappear. Take the derivative of c, you get 0. That leaves you x e to the x. That's exactly what we had. Yeah. Okay. There's that one. Now, they went through a process of doing it the other way and showing you that it didn't help you any, okay? And it got worse and worse and worse. So don't go that way. Make things get easier, better. Be lazy, right? Okay. Now, there are times, and I already hinted at this, okay? There are times when you don't get everything to work the first time. So as long as it's moving in the right direction, try it again, okay? And here's what we got. We're trying to integrate x squared cosine x dx, okay?
Do you happen to be able to do that just by inspection? No, I can't either. Okay? Substitution? No, can't do that either. So, notice this is a product. So maybe integration by parts might work. Which one you want to choose is what? Say again? X squared and dv equal cosine x dx. Always keep the d's together. Okay? Then, what does this become? du is equal to 2x dx. And dv equals, v equals sine x. Got it. Antiderivative of cosine and sine. All right. Now we proceed. This will be x squared sine x minus the integral of, I'm going to pull the 2 on the outside, and it will be x sine x dx. Right? The bottom line, what you got there. d du. Integral of, pull the 2 on the outside, 2 times the integral of x sine x dx. Okay? Can any of you do that integral? No. Okay? But guess what? We can do the same procedure again. Now, if any of you have objections to using the same letters, you can use different letters. But we're so used to letting u be something. Where did the negative come from? Yeah. It's because, really, from the product rule, when you take the derivative of a product, you have this plus this. So if you separate one of these over here, subtract the other one from that. So that's a minus. Say again? Okay. Why did I factor out the 2? Okay, maybe okay. The du, when you take the derivative of u is x squared, derivative of that is 2x dx. Is that what you're asking for? Where the 2 came from?
Yeah.
Oh, okay. It came from derivative. You're choosing this to be your u. You got to get a du when you take derivative of this is 2x times derivative of that. Change real tight. Oh, why did I factor it out? I mean, what I was writing over there is this here, d du, which would be the integral of sine x times 2x dx. Well, the 2 is just a constant, so I pulled it on the outside. I just rearranged the word. Yeah. Okay? It's this stuff in the bottom line.
You just take the 2 outside.
Yeah. Right. Okay. So we still can't do that integral, but it got simpler than this one, didn't it? So let's try it again. So everything else is still there. Let's just do this integral right here.
And what do you think you ought to do? Let u equal x and dv equal sine x dx. Okay? Then du is equal to dx, right? Right? And v is equal to cosine x dx, but I think yeah, that's right. No, integrating, yep. Eat this thing. Okay. I believe that's a minus there, isn't it? Derivative of sine is cosine. The integral of sine would be minus cosine. Right? Antiderivative of sine is minus cosine. Because derivative of cosine is minus sine, so you'd have to have a derivative of minus cosine would be positive sine. Okay? So what do we do next? Now remember, don't forget the first part. You already have the x squared sine x minus 2 times, and this is just doing on this. What do you do first? It's uv, so that would be a minus x cosine x, because that minus is there. Okay, then you do a minus the integral of your bottom, okay, except you already got a minus here too, so that makes that a plus. And that would be cosine x dx. Okay. So this is going to be x squared sine x minus a minus is plus 2x cosine x, right? Minus a plus is minus, and what's the antiderivative of cosine x? Sine x. Sine x plus c, because it's an indefinite integral, you got to have that. You don't need to put it in every place, just somewhere at the end, be sure you got a plus c. What's that? Oh, yes. That 2 is outside here, so that's going to be a 2 here. The c doesn't need a 2 with it, because it's just a constant. Yeah, that 2 is outside of that. Good catch. All right, you want to check and see if you get, when you integrate this, do you get that first integrand? I mean, when you differentiate this, do you get the first integrand there? Well, let's see. Integrate this, and differentiate this, and see what you get. Which way do you like to do product rule? First on derivative or derivative times first, second? I don't care. Take a derivative of that. 2x times sine x plus x squared times cosine x, that's the first term, plus 2 cosine x plus 2 times 2x, but it's a minus sine x, so that becomes a minus there. Remember, derivative of cosine is negative sine. Okay, so that takes us to that term. Then this will be a minus 2 cosine x, because you're taking the derivative of it. And then the last one's a c. Yeah, derivative of c is 0. All right, let's see if there's anything we can... Oh, there's a plus 2 cosine x and a minus 2 cosine x. There's a plus 2x sine x and a minus 2x sine x. And sure enough, you got that, and that's exactly what you had up here. That's just checking. You don't have to do that. But you know, I hate making a mistake. I make plenty of them. I like to check to make sure I can find them before I turn them in. We will not turn it in. Good deal. That was example 3. Integration by parts more than once. Is it time to go? How sad. Doesn't it make you cry to say that? What? Okay. We will begin next time. She's so big old, she doesn't cry. Okay. All right. We'll start next time working on definite integrals, not indefinite integrals, and we'll see what we need to do there. So that will be, let's see, is that the next slide? Actually, they did have a slide on that one step that we had. I could have used this, but it seemed like that was that first step where we did UV, U V prime V, U prime V, and then they took out the two. So yeah, they did it in 2 steps while I did it in 1. Okay. Next time we'll start with that slide. Good deal. We will end